Right, welcome back. Let's start with the session. So the first speaker is Bernd Siebert. And he'll give the second lecture on from toric degenerations to intrinsic symmetry.
Okay, so yeah, we stopped and I wanted to explain a little bit about this construction, the flavor of the construction when you start with this triple of polyhedral and interactive manifold with similarities, a polyhedral decomposition, and a strictly convex, maybe multivariate plus linear function. How to construct this degeneration x over, and then I have some s that conveniently just for this talk, let's just take the space and over t, but there are a few more parameters. So let's just do one example here to tell you what the fundamental insight is. So if we take two triangles, so two copies of P2, the momentum multiple two copies of P2, and we put a focal singularity at the center of the edge. And let's assume this, what I've drawn, is a chart when I cut over here. So it's really a chart at this point. Okay. That means if I go up here, the chart would look like this. This is how focus singularities work. Little exercise that everybody can figure out. So then let me give some homogeneous coordinates here. So these are the monomials in affine geometry. Let me make sure the notes here. So this would look like this. And now you just pretend there are no singularities and we do the toric construction, the Mumford degeneration construction. What are the equations you would get? Oh, I haven't thought what phi is. Let's take the minimal phi that has just changed the slope by 1 along the central edge, okay? I'm not writing it. So what you see here is a W doesn't do much to the equation, but you get an equation xy equals z squared times t, or t times z squared. Okay, so this would be the toric models. While here you obtain something different. If you compute xy, you get tzw. Okay, so obviously we did something different. We should get something different. So that of course doesn't match. So the singularities of the affine structure make these the Mumford construction, of course, inconsistent.
Sorry, what's in this first equation? Is xy equal to
T times z squared. I'm sorry.
t, and t is the parameter of the
T is the parameter
okay,
over here, right? It's just a Mumford degeneration. Okay, so we correct by walls to make that thing put this in quotes and not only defining this. But what will happen is the following. So let's now do the following and put a correction factor here, which at this point is 1 plus t w over z. Sorry, 1 plus w over z. While here it's 1 plus z over w. So the correction factor would work, would correct this equation by putting in a multiplicative factor. So then on the left, I obtain xy equals t times 1 plus w over z times z squared. Well, this is t times z squared plus wz. While over here, I obtain, the point is I've done the computation here, right? That is this computation. While if I do the computation here, I obtain still xy equals t times zw plus, but then with the correction factor 1 plus z over w. I've done everything correct, it should be the same thing. Maybe I should change the order. CW plus C squared. Okay, so this is a fundamental idea. You put in close to start by correcting close to the discriminant locus by putting in factors that are very easy to write down in these kind of simple singularities case, and it will make the whole thing locally consistent. Okay, so you do this, and then of course you immediately notice, of course you can't correct something locally without the change propagating, and this is how walls will propagate. Okay, so the walls that I was talking about is really this kind of thing here. So that's a wall. That's a wall we have started to put in. Actually, stops here, of course, right? So let's do something slightly more global. Let's assume we have 4 two-dimensional cones coming together in this shape. So I could give some coordinates here. Let's say let's take x, y, z, w. Okay, and let's assume I put in singularities of the upright structure. So this little thing here, over here and over here. So of course, I mean, this is part of a bigger picture. You could put vertices here, okay, and then close it up, whatever. We're not discussing this at the moment. But as I've told, there's these walls. Wrong color. That I'm now thinking of propagating in these directions. Yeah, the monomial that you get here is the equation of that P1 that you see in the middle. So Z over W is the coordinate of this P1 at this point. And it travels in minus that direction where the monomial points. And then what you see is, so what you put here is, what do I say? This now in affine coordinates, okay? This is a little w. So here I would put a 1 plus w. Here I would put a 1 plus y. Then of course I have to continue. Oh, I should give you the equations, right? So the toric model would give you the equations x, y equals t, and zw equals t. Okay, so this means the naive guess is what you should certainly do is continue with this wall with the same monomial. 1 plus w, well, if you want to go far away, then w doesn't make sense anymore because it lives here. So maybe it's better to write this as 1 plus tz inverse. 1 plus tz inverse.
So at the origin there is 1.
Yeah, the value of the thing is 1. Yeah, that's true.
And 1 in your correction factors is it? So what's the meaning of 1?
That's a distinguished number. Yeah. There's always 1. There's a normalization condition where we ask that at each vertex the value of these corrections are 1. Okay.
So it's actually 1.
It's actually 1.
So it's not a monomial 1.
No.
It's a number.
It's yeah. You should think as x of something else. Okay. The exponential of some function. Exponential of a monomial. It starts with 1 plus whatever. It's a multiplicative unit. That's how you should think of it. Okay, so then over here, you do a similar thing. So you get a 1 plus y, which I could rewrite as 1 plus tx inverse. So then you do the computation around that thing. So you change charts here, 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 and come back, and oops, that doesn't work. Okay, obviously there is something because of the non-commutativity of this group of automorphisms of the torus. It's that won't match. But then you observe that there is a way to fix this. Namely, you can insert more walls. So we make this. So we make this consistent by inserting more walls. So the wall that I'm introducing here is this one. And it will have some monomial 1 plus, well, it's essentially a YW, but maybe I should rewrite this as 1 plus T squared Z inverse X inverse. And then you do the computation and actually it works, okay? So it's a little computation that you can do. It's fun, or maybe not so much fun, but it comes out, okay? The picture is slightly misleading. So this would be good for all orders, okay, all T orders. It's slightly misleading because once you change these a little bit, let's say you start here with Y cube and W cube, you will have to keep inserting walls. So the typical picture is not like this, but it will have actually, depending on T order, it will produce more and more rays here and maybe even fill a dense region if you want to make it consistent in higher and higher order. Okay. So, but that's the flavor of the game. So you insert walls, you check inductively in T order that you are consistent, and then it works. So this process, this scattering here, that has been done by Kontsevich and Seudelmann in dimension 2, and Mark and I generalized this to all dimensions. But the fundamental thing is still this scattering dimension 2.
So you say that there is a theorem that eventually ends.
Yes.
So
if you know what to prove, you can prove it. It's not hard.
The statement is that it's not that for every order of T we can make it agree by inserting more walls, but rather than we insert finitely many walls and then it agrees up to any order of T, or no?
No. So you fix a T order.
Yes.
And then the statement is that you can make it consistent uniquely by uniquely inserting walls up to order K.
Okay, that I agree.
So it will not be consistent to all orders typically.
And it's downward compatible.
Excuse me?
It's downward compatible.
Obviously, because if you the group modulo T to K plus 1 is compatible with taking.
But you're saying that for a fixed order, you need infinite.
No, for fixed order you need only finite dimension. Yeah, that's important. Okay, so what one obtains from this something what we call SL. L is my T order, yeah. So modulo T to L plus 1, consistent. Maybe one more. So this consists of, so each wall consists of a codimension 1 polyhedral piece. Inside some sigma, yeah, which is some maximal cell of your polyhedral decomposition. It could be let me just try like this. And then some Laurent polynomial. So this is a Laurent polynomial of the form 1 plus or whatever. Okay, so let's not be too precise what exactly we get.
You start to choose really complicated letters. I can't write. Okay.
It's a P. Take whatever fancy P you know. Okay. So I should say how these FPs, so that's the function I've written here, right? This is my FP. This is the wall. And so the automorphism you get, so each wall produces an automorphism. So it's this kind of, let me write it in dimension 3. Yeah, so this is my P here. And then whenever you kind of cross in this direction, you obtain an automorphism. From wall crossing which is of the form, so it's it's a little theta p that goes from that in this case. Let's take it over here, right? It goes x to fp times x and y to fp inverse times y.
It's an automorphism of what?
Of this formal torus that you have, of the toric model. Yeah, that's the automorphism of the toric model. So the one you get from the Mumford construction. Yeah. So for example, you could take C double bracket T and then the Laurent polynomial with x plus minus 1, y plus minus 1. Yeah? That would be the automorphism up here when you go from here to here. And the power that you obtain here has to do with how this monomial relates to the wall. Okay, so there's a normal vector, and you evaluate the monomial on the normal vector, and that gives you this power. Okay, this is why this has a positive one, this is a negative one. Okay, so and then we define XL, an nth order thickening of X0. By taking the limit over some pieces. There's some complicated decorations that I don't want to write. So essentially, what are these? This is thickenings of toric strata labeled by the connected components by what we call chambers. These are the connected components of B minus the union of the support of all these walls. Yeah. So these would be this one, you get one chamber here, you get one chamber here, and so on, right? These are the chambers. Your walls decompose your B into chambers, and then you have each stratum get thickenings inside this chamber, and you take the colimit of these, okay? And that produces a consistent thing that works over spec C, T mod T to K plus 1. I wanted to turn L. L's order thickening, yes. Okay, so in the end, of course, you get only a formal scheme.
So the most complicated thing for me in this whole procedure that I never fully understand is, at this point, why do I not have holes in the space that I constructed? Because it seems like I'm only constructing formal neighborhood, gluing formal neighborhoods of the torus.
No.
So you're adding something more there, right? That's the part that
yes.
I
And each. So let's say for this point, I also have a toric model, and then if I choose it, so actually it's a pair of two strata. So you take this stratum and that stratum. Let's not be too complicated. Okay, let's take this stratum, and then for each wall you get a model. Okay, you patch them together by these wall crossings.
But the model
and
is
that
not...
gives a thickening of this point.
Yeah.
And then similarly, you have a thickening for this stratum, and a thickening, and they glue everything together. Okay.
But some of those thickenings are not just this trivial.
No, they have some more. So you have to replace this by some toric thing in here.
So just to understand again, because I also never fully understood. So for each open chamber, you have a torus.
May I interrupt you? We have a lot to do, okay? So this is not essential. I'll give you a better way to construct the thing in a second. Okay? You don't need to understand this to follow the rest. There's a way to construct this thing by patching toric pieces, okay? We can, I'm happy to explain in any length after the talk, okay? I don't want to get stuck down by inessential stuff at this point. So this goes to, this formula. Okay. Then you could, in the Calabi-Yau case, you can use Grothendieck existence to actually get something better, but there is a much better way to do the whole thing. Namely, we can produce these theta functions. So we can produce a homogeneous coordinate ring by just hatching codimension 0 and 1. So there are only two models. This is this one, and the other model looks a bit like this, okay? You have two monomials that you multiply, and it's a t power times some wall function. Okay, these are the only two models you need, and then you can construct these theta functions. And they are functions on this homogeneous coordinate ring. So construct as functions on, well, it is essentially this kind of x on x minus the codimension 2 strata. Okay, so it still makes sense to do multiplication on the thing, so it becomes a homogeneous coordinate ring. How does one do this? Via what we call broken lines. So that's a very cool game. Well, I'm lying again a little bit, okay? So broken lines, if you really want to construct sections of these polarizing line bundle, you can't work on B, you need to work on what corresponds to a total space of O minus 1, okay? You go over to the cone, so rather than working on B, you work on this truncated cone, and then you do this, okay? So this just for peace of mind. In the case where we actually construct something like actually functions on the thing that also exists sometimes, it's literally broken lines. So let me look at this. What would be this thing here? Okay, so let's look at this scattering diagram, and I'll show you how to construct distinguished functions on that. You will get a function for each monomial that is kind of asymptotic. So let's start with this monomial. So that was W down. So I take the kind of the minus W monomial, and I think of this coming in from the bottom. We had one more wall. Let me just draw them all black. And the functions we had associated with 1 plus y, I'm just using these coordinates, 1 plus wy, 1 plus w, or 1 plus w. So let me construct theta w. So broken line would start here, somewhere in the w direction, and each time it hits a wall, you apply the automorphism associated to it, this kind of guy, okay? So what this will do to w, it will turn w in w times 1 plus y. So this here is a w times 1 plus y. Then you expand it into monomials. And each of these terms tell you how you could continue. So the first one isn't doing anything, just continuous. The other one is a wy that would go in this direction. So this one has a w, this one has a wy. And then the theta function is a function that you obtain when taking any point inside a chamber. So you want to express the theta function as a function in here, as an element in here, okay? So you take a point here, and then I look at all broken lines that end here with asymptotic w. Of course, this is not good, but there's another broken line that will end here, which is the one coming from here, right? So this is a w. So the theta function at this point, the theta w, of course, theta w down here is just w. Theta w up here is, what did I say, w plus wy. And then let's do something different. Let's see what we get when we are up here, because that's really the fun. So why should this be consistent? Again, you have one line that just goes through. Then there's another line that could come here. Okay, so this gives the w and the 1 plus w, the yw. But there's one more, because now we still have a non-trivial wall crossing here. I'm not writing it, and that comes from scattering that line at this point and picking out the wy. So this would be a w squared y. And then the whole thing becomes the equation theta w is w plus wy plus w squared y. And you can check that the theta for this p actually maps that one to that one. Okay, so that's the idea of producing theta functions. So whenever we have these diagrams, we have the basis of whenever it's this wall structure, we get this number. Okay, so maybe now I can stop for a second. Does this roughly make sense to everybody, or just structurally make sense? So we have said we by introducing the singularities, the toric recipe, the Mumford degeneration recipe will be inconsistent. We fix this by inserting walls. Once we insert the first walls, that will fix the whole process locally near the singular locus. To globalize, we need to continue with the walls. And then when walls hit, you need to insert more walls to make it consistent at this point. Then we get this complicated wall structure that has all these monomials. We use this to build up maybe an nth order thickening, but only away from coordination 2. That will be enough. Okay, where was the coordination 2 thing? I wrote coordination 2 somewhere here, right? So we construct this. Oh, so maybe I should just write XL here actually. So which is to get glued together from just these kind of thickened tori up to order L, of course, and then the other ones that is of the form xy equals t power times some function. The t power, by the way, is the kink of the phi. Okay, so that tells you what t power you put here. So that gives us a space which is non-compact now, right? It's non-proper. It has we remove the coordination 2 strata, but nevertheless we can produce a ring of functions on it by this kind of procedure. And that will restrict to the correct ring of functions on the central fiber. And then I take the approach. Questions?
If you're imagine like you're on S2, right?
Yeah.
Trying to keep this K3. So you would fix a point, then your theta function would it be finite number? Way to get to this point.
Finite number? You mean?
I mean, the number of monomials.
No, I mean I've written it like this. So these are t order 0 is just w still, right? This is actually this has a t. What was it?
Every time you cross the wall, you get t.
You get at least a t.
So you would get only finitely many.
You get exactly in right. Yes. So in each t order, you get only finitely many. Yeah. But these are analytic functions. We get the Riemann theta functions, right? That I talked this last time already. So if you just run this, I mean, there's no scattering, but still, you run around, and of course, you just get the theta series.
So the functions are functions on this formal torus, or what?
On here.
The functions of what? On what?
Well, on the total space of O minus 1 restricted to this complement of codimension 2.
Because he needs to do this in the cone, right?
Yeah, I need to do it in the cone to get to construct sections of line bundle as functions. Okay.
This direction W is somehow an unbounded direction. In the compact, you have a compact thing. W is the unbounded direction.
Okay, so let's continue. So historically, so this was the kind of one kind of original GS, and let's go to intrinsic symmetry. I'm skipping here historically a number of developments that lie between the 1 and the 2. So there was first this tropical vertex paper of Margni and Rahul Pandre that made the connection that gave the interpretation of this concept of Solomon scattering diagram in terms of curve counting on toric surfaces. Okay, so by that time we knew we were on the right track. We have some enumerative interpretation of our wall structures. And ever since we thought of wall structures as capturing somehow counts of disks. And actually that's where it's coming from in a way, right? So Fukaya had some early fantasies in this direction. And that is a kind of the correction. So, and then Mark with Paul Hacking and Sean Keel changed the philosophy and used that construction to produce mirrors of surfaces that are non-toric, essentially blown up toric surfaces. That is kind of already in here, but the switch of philosophy really happened in this paper, and having cool applications. So, and then there's Gromov-Witten theory that was kind of developed in parallel and coming here from the GPS paper essentially. Actually, all that I wanted to do log Gromov-Witten, and then punctured Gromov-Witten theory that we developed together with Dan Abramovich and Sheila Chen. We were ready to say, hey, let's get rid of all, kind of rid of all, but not quite, but let's refine this and get something a lot more general and more interesting. So this provides canonically mirror geometries for all cases expected by algebraic geometry, expected by algebraic geometry, and maybe even a few more, and some more, in a way compatible with the old GS. It's also a little bit of a lie. There's a technical issue, but morally, I'm sure it's correct. Okay, so we have proof that technically that these are really exactly the same thing, except in special cases. We're sure it's true. So there are two cases. Let me just give a few such things. So let's assume that we use this fancy X to denote a family of Calabi-Yaus, proper Calabi-Yaus. Let's say we have a smooth family of complete Calabi-Yau over the complement of a curve minus a point. Okay, so this could be the spec of a DBR, for example, also something a little bigger. And I want this to be maximally unipotent. So that already came in the talk of really the setup that Javier was talking about yesterday. So which means that T minus identity to n non-zero. Maybe you want T power also, T to k or something. And then there's a procedure that produces a y, which is the proj of this intrinsic mirror ring. It's really the ring of theta functions that we will produce here, okay? But we produce it in a different way, a slightly different way, over the formal spectrum K that we bracket. Sorry, not. K of a completion of the cone of effective curves on X. X is a, yeah, maybe I should write curly X over S or something. The relative curves. Okay. The other case is the absolute, so that's the relative case. And then we have the absolute case where we work with Calabi-Yau pairs. So we have an X comma D. Oh, to go here requires exactly using these papers by Nicaise and Xu and Yu, etc. Yeah, so that's how we mentioned yesterday.
Here means where? To go here.
Yeah, we first have to get a good semi-stable model, and then we do something to produce that. I'll try to sketch this a little bit, but this is where this comes in. So let's say we take a normal crossings pair, and I assume it's weakly log Calabi-Yau. So classification theorists would always complain loudly that this is not Calabi-Yau for them, but it's Calabi-Yau enough for us. So I just assume that Kx plus D is linear equivalent to some AI Bi. D is this divisor, and I want the AI to be larger or equal 0. Okay, and we want it maximal. That just means that we have a zero-dimensional. D has a zero-dimensional strut. And then what we get is, in general, really only a formal scheme. But if X minus D is affine, so if D supports an ample divisor, then actually the whole thing is algebraic. Then so this really lives over. It's very big. It's a big family. It lives over the spectrum of the corresponding. I'm writing any X. Of course, any X may not be finitely generated, so you may want to base change to some finitely generated overing of the thing. But in any case, so you get this algebraic family or big kind of toric variety. So how do we do this? Yep.
In this relative case,
yep.
What is this arrow? It's algebraic or it's formal, because I cross algebraic above and formal below.
This
the
one?
vertical arrow.
Oh, I'm sorry. Sorry, no, this is not. Sorry, this is, what am I doing? This is a spec.
So it's a genuine spec.
This is really algebraic.
Yeah, but the ring is the formal power series ring. So
yeah.
I could think of it this.
Yeah.
Okay.
That's the wrong line, I guess. Okay, so yeah, so how does this construction work? The point is, so Javier essentially told you yesterday how to get this. It's the same process we do. We get this skeleton. So we get the skeleton that we now call, I forgot what the notation was in your talk, but this is now our B in the dual intersection complex. Okay, so sigma was the dual intersection complex, which is a simplicial cone complex. We work with cones. Maybe that's slightly different. Simplicial cone complex. Oh, let me do A for simplicity. In this case, we have an additional grading that helps to make it a little more finite, but the principle is the same. So we have this skeleton B, and because of these statements, Nicaise, Xu, and so on, this is a pseudomanifold. Okay, it may not be a manifold. Maybe let me know, right? It's a convector, but we don't care. Okay, so but it's a manifold in codimension 1, and this is all we need for this kind of scattering procedure, if you remember. And now we produce a let me do so this B and sigma is a considered Solomon skeleton of the stuff where so this is spanned by those where the AI are 0. Okay, and then this thing has an affine structure in outside codimension 2. Outside codim 2. So I just have to tell you what the affine structure is when you pass a codimension 1 cell, and that's done by these intersection numbers. So whenever you look at di dot c and see the curve, that will tell you, if you know a little intersection theory toric varieties, you should be able to guess what I mean by this. Okay, if you the way you pass through a codimension 1 cell tells you like the king along this codimension 1 cell tells you the intersection number, and doing that and then looking at it correctly, you can get this affine structure. So let me show this in one example. Give you a little better idea on how this works. So let's say we take P2, we blow it up non-torically in one point. So I get some exceptional curve here. But D will be the one. D is the union of these three divisors. This is my D. So what do I get from this? It looks like the fan of P2. And the affine structure is also correct here, because we haven't done anything to the intersection numbers here or here. But here it's not correct, because you blew up that intersection number, the self-intersection number drops to 0. And that translates into the affine structure to make that kind of line straight. That line straight when I look from here. Okay, so it's a little exercise in toric geometry to figure out that this gives the correct intersection numbers. I won't have an affine structure here. Yeah, you can't flatten this out. So now we have changed the philosophy slightly. That is actually contained in GHK. That we don't have the singularities at the centers of the edges, but we push it all in codimension. Theta functions and so on still work, as long as I have a wall structure. So how do we get a wall structure? Okay, so the consistent wall structure comes from log Gromov-Witten theory. So I'll have to wave my hands because I don't have time, and I don't think that's maybe quite the right audience to expand on this too much on log Gromov-Witten theory. So so what is log Gromov-Witten? So Gromov-Witten theory is based on stable maps. See diagrams like this, right? Log Gromov-Witten theory just puts in a log structure at each point. Okay, easy enough. There are some subtleties which log structure is the correct one. Trust me, there's a good choice. And so, for example, this could be e.g., it could be a log point. So there's some monoid, a toric monoid. And it already has some, the thing is, there's interesting structure already over point. Okay, so over point, you work here with a log point rather than with just a point. There's this additional monoid, and that has some cool feature, namely you can tropicalize. There's a functorial notion of tropicalization that turns diagrams of log schemes into diagrams of cone complexes. So this produces a cone complex, let's call it gamma C. Then this is gamma X, which actually is just a dual intersection complex in our case. So this is our sigma. And then here is a Q dual. So tropicalizing the log point just produces this dual, the kind of cone that you would get in a fan of a toric variety. So that's a map of cone complexes. So it's a diagram of cone complexes. That thing here, forget about this. So that's the tropicalization of this map. But that thing here is a map, is a tropicalization of a map of a curve over some base. It turns out that is a family of metric graphs. So this is a family of metric graphs. Let me try to tell you how this is roughly done. So for example, I could look at that thing here. So this is my cone complex. I project it down. So this could be gamma C, and would be Q dual R if we have a standard log point. And now you see that the fibers over each point is an integral affine curve, also known as a metric graph, right? So that's a metric graph. It's an abstract tropical curve. So if you do log Gromov-Witten theory on such a pair, this comes with a log structure for the pair, and you tropicalize, you get families of tropical curves on your dual intersection complex. And if you're careful enough, you end up in B. Okay? So the walls are obtained by doing certain restricting to a certain kind of tropical curves or stable log maps with restricted tropicalization. So how does this work? This is very rough, I apologize. So these moduli spaces of tropical curves, of tropical stable, what am I saying? Right, so you have a moduli space of tropical stable maps. You should think of tropicalizations of logarithmic stable maps. They provide a base Ardian stack replacing for log Gromov-Witten theory, replacing the stack of pre-stable curves in ordinary Gromov-Witten theory of nodal curves, right? Pre-stable curves in ordinary Gromov-Witten. Okay, so you have this modular space of stable maps, stable log maps. That goes to some moduli space of tropical curves. So maybe I should write M of sigma, okay? It really has nothing to do with X, it only has something to do with sigma. There's a way to turn this into an Ardian stack. So this is the moduli of tropical curves. Is this guy? No? Okay, so then whenever I restrict the types of tropical stable maps, let me call this tau, I obtain a pure dimensional subspace in here. Okay, so this is a pure dimensional substack. This is virtually smooth, so this has this relative kind of, whenever you have something pure dimension, you can do a virtual pullback, and that gives you a virtual fundamental class of this m tau sigma. That gives an m of x tau in here, and that contains carries a virtual fundamental class. Okay, so what I've tried to tell you is that whenever, so what's the type of a tropical curve? Well, it's what we think it is, right? So tropical curves come in families, they have a certain combinatorics, the type fixes that. Fixes the combinatorics, fixes the directions, fixes how you meet the strata, and so on. To get the walls, we look at tropical curves of a certain type, namely of wall type. So for walls, I get wall types tau. So what should be a wall type? Well, it will be something that starts somewhere in your diagram. Then it will produce some go off and end at some point. So this is some start point, there's some bunch of vertices, and then it stops somewhere. So end point, it has one end point. And I want the tropical family of dimension n minus 2, and the end point to vary in dimension n minus 1. So it actually sweeps out a wall. Yeah? So you can imagine there are certain tropical curves on sigma that happen to sweep out a wall. Okay? And I take all those, I get log Gromov-Witten invariants.
Yeah. So you're saying tropical curves, but these are actually Gromov-Witten, like they actually live in the total space.
No, sigma. That's sigma.
So just
this is really tropical. It's as naive as you think. It's discrete geometry. It's doing something on a cone complex. Let me give you just this one.
The things will come. What is it? Slab functions will come from the upstairs counts.
Yeah. Let me get this thing here. So here's an example. Essentially the one we did before. So the blown up, this kind of blown up thing, right? You see there is a curve here that is a strict transform of the line through this point. Certain curve that produces a log Gromov-Witten invariant and actually produce one wall function. So this was your sigma, and the wall you obtain from this curve actually is as simple as you get. It starts here and it goes out. This is a wall, right? This is a tropical diagram, right? I can draw this. And it turns out the invariant is, I guess, 1 or something. And then there are multiple fibration that we also show. How do we, let's relate this to our old GS story. How would we do that? I mean, of course, you can't really do GS here. There's no degeneration. We first have to put in a degeneration to get this into the correct shape. But we can. And in this case, so you would have to subdivide somewhere. Maybe I don't know. Just put in something that you like. Something like oops, good. Maybe like this. But then you put in a focus singularity here, and it will produce walls here, and then it continues, okay? This diagram, actually there's another one that which comes from the exceptional curve. That diagram is related to that one by moving that singularity in here. Okay, this is how these two pictures are related. So the upshot is, I have like 5 minutes for one comparison. Great.
I can make you an offer. I can leave you like 10 minutes at the end of my first talk.
Okay. Let's see.
What's the price?
No, just so that you don't rush. That's why I said this.
So let me carry these points home here. So this gives an enumerative interpretation of the walls. We also have enumerative individuals. So walls look like this. Let's forget about these tentacles that go off here, okay? But also of these broken lines. And even so, broken lines would have one incoming thing, and then I pass through, and then one outgoing. And also of the multiplication rules, coefficients. So in this case, you would have two incoming things. You could formulate this also in terms of kind of broken lines, multiplication rule for broken lines, and they look like this. And the second thing is, this was kind of historically came slightly later, but this got published earlier. The other one is still not published or accepted. We can also define the ring structure directly without ever talking about B. Sorry, that's not quite right. Without ever talking about walls. Without walls. Maybe I should also mention that we announced this in 2015, and after that, Kiel and Yu started working on a rigid analytic approach to that. And they would just came out. They had one paper where they assumed that x minus d contains a torus, and now they have the case where x minus d is affine. Just came out maybe last week or so. So, but they don't do anything virtual. They have a kind of more direct enumerative interpretation. Okay, so I think that it's a very good state of affairs, because it brings in the kind of the beginning of the whole subject, namely curve counting, into the very construction of the mirrors. I think that was a big riddle. I mean, how would that ever come about? And now in the end, hey, it's built right in, right? So you start with curve counting that gives you a mirror. Sure, there should be some kind of relation between the enumerative geometry and these things. We haven't proved that yet, but at least we have the right. It's not a miracle anymore. Let's put it this way. I'm not sure. Do I have 5 minutes more? So let me tell you how we imagine to prove homologic converse symmetry. So I start with this family, let's say analytic, and X is a general fiber. That gives us the symplectic monodromy. So the whole thing is KR, let's say, embedded in some projective space or so. Let me call this phi from X to itself. And X is a general fiber, so this just goes around circle, large circle or small circle, whatever you want, okay? There's a very traditional subject that is at least 30 years old. It goes back to all the way to Fleur. There's a fixed point Fleur theory that produces a ring that we call S of phi by taking the fixed point Fleur theory of phi to the power of d larger or equal to 0, and turns into a ring with a pair of pens product. So what are the generators of this? The generators are fixed points of phi to d. Or actually, I should put a 0 here, okay? So the generators is something like H0 of the, or maybe C0 of the fixed point locus. So on a project with Tim Perutz, so of me with Tim Perutz is there exists isomorphism called a log PSS, so Newton, Solomon, Schwarz, isomorphism from R to S of phi. So for people in the know, so the PSS that was what came up in Chirion talk yesterday. That gives you isomorphism between Hamiltonian fluid theory and quantum cohomology. Okay, that is how this came about. So, and it counts, the morphism would on one side take these intersection products or end at a cycle, and on the other side end at a fixed point of the Hamiltonian. Okay, so we modify this slightly. So the fixed point, so the cycles that we take are just the generators of our intrinsic mirror ring. The generators of this intrinsic mirror ring are strata, so contact orders. These are the monomials, the m's. Okay, they have to do with contact orders. And then we count. We count this. Well, maybe I shouldn't draw it like this. Maybe I should draw it like this. We count disks that cover the space, my S. Sorry, D. D is not the divisor. Okay, same problem as yesterday. And then they're asymptotic to the fixed point. This is for D equal 1. Okay, for higher D, you would need higher D would go like here, and then you need some kind of 2 to 1 cover or whatever D to 1 cover. So this map would take this contact order. Let's call it little p, or sorry, it was an m, right? Let's take m. This is a contact order. Let's say D equal 1, so that's an integral point for D equal 1. Would just be an integral point of B. We take a general point here. This gives the generator theta m, and we would map theta m to exactly this fixed point locus. So this is a component of the fixed, corresponding component of the fixed point locus. Okay, so and then I have like 4 lines to tell you how to get to homologic mirrors here. And believing that this is true, that this is actually an isomorphism, then the problem is purely symplectic. Okay, now we have gotten rid of algebraic geometry, we have gotten rid of log geometry. It's a purely traditional symplectic geometry question because we are talking about symplectic geometry on a Calabi-Yau, let's say 3-fold, or a Calabi-Yau n-fold. And that is still a little subtle. So the first thing is you need some, so this symplectic monodromy ring, we need to get to Lagrangian. So how do we get this? If x to d comes itself from gs, we have a positive real section that is actually Lagrangian. Okay, so this gives some family of Lagrangians LT in xt. So these are Lagrangians. And we take these as kind of generators of the Fukaya category, or rather we take these together with all their monodromy shifts, translates as generators of the Fukaya category. By the way, this also has a good fluid theory. Fukaya showed that they're demonstructive. These kind of real low size. So and then there's a closed open map, which also was featured yesterday in some version. So it goes from the symplectic monodromy ring to something like a part of the fluid theory generated by these powers of these translates. So let me write this as HF plus of L phi. So it's a direct sum of HF Q of L phi P of L. So, and we take P larger or equal 0, but Q could be anything. The notation suggests some Hodge theory, okay, and it actually is. So there's a statement of Polishchuk Well, this is very close. So in here, by this isomorphism, right? So we have this R in here. Where does this map? This maps to direct sum kind of, well, this is like the direct sum of H0 of L to D, yeah? Or O of D. P. I've changed notation, okay? And that maps in here, so that maps to the Q to 0 part. And Polishuk has a little algebraic theorem that this map of rings has a unique extension to an A infinity isomorphism from direct sum all P, Q, H, Q, O, P to this HF plus, to HF. I mean, where I take all the P's and Q's.
Polishuk has which Polishuk? Like which
Alexander.
Polishuk? No, I know.
There's I can give you the reference.
symplectic theorem.
No, it's not right here. It's about infinity structures on rings of this form. Okay, or on. Yeah. I can show you the reference. So and then the last step is an automatic degeneration criterion that tells you that if you have such things here, that's enough to prove homological mirror symmetry. So there are two versions of this. So it goes back to Abu Zaid, I think. Told me this one before it was published, I guess. Things and Ganatra and Perut Sheridan. So various versions of
And
this.
Sanda.
I don't know this one.
That's the actually published version.
Of who?
Sanda is a
These are all
Japanese guy, I
published.
think.
These are all
No,
published.
Ganatra's papers are published. Perut Sheridan is not what you're going to say.
It is.
Smoothness, you're going to talk about smoothness, right?
That's in here. Wait, who do you want me to put?
Sanda, I think.
How do you spell it? I don't know.
Sanda.
Sanda.
I think he independently came up with this and has
Okay.
a published paper, so he should be cited.
Okay. Yeah. Okay. I don't know this.
Huh?
What? Okay. So and then we have DB code. This statement is in Perut Sheridan. That is equivalent to d pi fs. And that indeed needs smoothness of the category, okay? So that's a little bit of a headache. Needs smoothness of R. So that puts a question, poses an interesting question. I mean, we produce these mirrors, and in the original GS, we have good control of the singularities. In intrinsic mirror symmetry, we don't. Right? So and typically, I mean, we know many examples where the mirror is not smooth, and that will be an obstruction to this kind of homological mirror symmetry statement. Okay, so but I went 8 minutes over time. Sorry about that. Oh, I should also mention that Dani Pomigliano has a similar. I mean, from the flavor, it's similar. This kind of scheme that you have some section and so on, but in the in using SH star symplectic homology and similar arguments to prove homological mirror symmetry for the case for the absolute case. Okay, sorry for going over time and.